Good evening, everybody. This is Mr. Mullicash. This is going to be our, well, it's good evening for me. It may be good afternoon or morning for you whenever you're watching this video, but this is our Math 171 Week 13 video for Johnston Community College. Again, this is my email address. Please contact me if you have a question about anything you see in this video. Of course, priority is given to my online students for Math 171. But this week we're talking about logarithms. It's a kind of a weird word, logarithm. So we're going to talk about what that is and some of the properties involved and some of the operations that are involved with logarithms this week. So without any further ado, let's go ahead and get started. The first thing we need to know about a logarithm is why we even have one to begin with. Okay, so don't know how that got there. Let's say that we have an equation 2 times x equals 6. Certainly everybody watching this video knows that x is equal to 3, right? And the way that you can do that is you can divide by 2, because dividing by 2 is the inverse operation of multiplying by 2. And we talked about inverse functions some last week, right? So again, the reason why you're dividing by 2 is because that's the inverse of multiplying by 2. But if we had something like this, let's say we had 2 to the x power equals 6. We need to find a way of inverting what was done here to figure out what x is, right? So if we think about that, we start with x, right? And we say, okay, you take the base of 2 and raise it to the x power. This, by the way, is called exponentiating. Exponentiate, right? With a base of 2. So anyway, you take your original input and you slap it as an exponent on a 2 and you get 6, right? So if you're thinking about solving this, okay, what have you got to do? You have to take 6 and figure out what is the inverse operation of exponentiation. Good question, isn't it, right? But if you can figure out that operation, then you can figure out what the x was, right? So you start with 6 and you do something. And so when you're first presented with this question, you might say, okay, maybe I should take the x root of both sides, right? You know, the x root, instead of square root, you could do the x root. Certainly you don't want to divide by 2, because this is not 2 times x, it's 2 raised to the x. So, you might say, oh, well, I'll just take the x root of both sides. No problem, right? So that x and that x cancels out. Now I have 2 equals, that doesn't really get me anywhere, does it? And, you can go on and on with this. You can write this as 6 to the 1 over x, but you still are kind of like bumfuzzled on how to figure out what x is, right? So that is the purpose for logarithms, because a logarithm is exactly the inverse operation of exponentiation. So what we have to do is we have to define this x, which is an exponent, as a logarithm. And the logarithm is spelled log for short. And the base of the logarithm is this number 2. All right, so 2 is the base. X is the exponent, of course. And I've recently found out in the past year or two that this number here without an exponent or with a 1 exponent is called the argument. The argument. So the answer here becomes the input in the logarithm. And so the base is a little size, and the argument goes inside the logarithm like this. So in this new equation, this new way of writing it, x is still the exponent, 2 is still the base, and 6 is still the argument. But that's what x is. It's equal to log base 2 of 6. And there's a way of figuring that out on your calculator. And while I'm here, I'll go ahead and tell you, if you have your calculator handy, the way to do this is you're going to look for either one of two buttons. You're going to look for LOG or you're going to look for LN. Okay, so what are these buttons for, right? And you might say, well, hey, Mr. Mollicash, there's a base 2 in this logarithm. What are the bases here? Well, that's a good question. Log by itself means log base 10. This is called the common logarithm because we are comfortable working in base 10. Our number system that we use is base 10. We use the tens, hundreds, thousands, place values and such. It's common for logarithms to have a base 10. So it's so common, in fact, that if we just write LOG, it means that there's an automatic 10 for the base. All right, LN stands for the natural logarithm. And the natural logarithm is a logarithm whose base is e. And you might remember e from the week 12 video last week. We were talking about this crazy number e that is used in compound interest and continuous compounding, right? So, for example, if you wanted to figure out how long it takes to grow an investment to solve for the exponent in that compound interest equation, you would need to use this natural log, okay? But still, like, we only have these two options on our calculator, but there's a base 2 in this problem, right? So what you can do is you can take the base of a logarithm and you can change it to anything you want. You can change it to anything you want. So there's a rule. It's called the change of base rule. And here's the way the rule works, okay? If you have a logarithm with any base of any argument, I'll call this big M, then you can change the base to whatever you want as long as you divide with a new logarithm that has your new base, and the argument of this new logarithm is the base of the old one. Okay, now why is this helpful? Well, let me use the last example here. If we wanted to figure out what log base 2 of 6 is, we can do one of two things. We can make this log base 10 of 6 divided by log base 10 of 2, or we can say this is the log base e of 6 over log base e of 2. In your calculator, log base 10 is just log. We just talked about how that's the common log, right? And in your calculator, log base e is natural log. So that's what that is. And so let me go type that in my calculator real quick, and I'll tell you what that is. LOG 6 divided by LOG 2. And I'm doing this off screen here, but you can do it in your calculator too. Make sure you use parentheses properly, right, in the equal sign. This turns out to be 2.5849625, and probably some other stuff. And that may not even be a 5. It may be 4 with something bigger than 5 or bigger after it. But your calculator has to round off, right? So maybe your calculator's got more digits than that. I'm not sure. But so what, again, does this number represent? Well, it's the exponent. Remember, every logarithm is the equal to the exponent. It's the exponent that makes 2 as the base becomes 6 as the argument. So you can always check your answer by, and if you did natural log, it would work too, right? Natural log 6 divided by natural log 2. So you can always check your answer by taking your original base and raising it to this crazy number exponent. in your calculator and say, what does that equal? Well, it should be 6. So if I go in my calculator here and I do 2 raised to the 2.5849625, sure enough, it equals 6, which means I got the right exponent. So again, the solution to 2 to the x equals 6, in exact form, it's log base 2 of 6. But in approximate form, you know, by trying to figure out the decimal for this, approximately it's 2.585, you know, if you want to round off, right, 2.585. So that's the basic mechanics of how logarithms work. So there's a couple of things we're going to talk about here with logarithms, okay? So let's say that we already have a logarithm equation, something like natural log of x equals 5. We want to figure out what x is. Okay, remember that this natural log is a logarithm. This means log base e of x equals 5. So where's the base in this equation? The base is e. What's the exponent in this equation? The exponent is 5, and the argument is x. So the answer for x is e to the 5th power. And if you want the the approximate value of that, you can raise e to the 5th power in your calculator. Normally, in your calculator, you can find e next to the natural log button. Maybe you have to do the second button, but it's like e raised to the x or something like that, e raised to something, or e by itself is usually the inverse of the natural log, right? So you could do second natural log probably and get e raised to something. So anyway, this turns out to be about 148.413. So the natural log of that huge number is 5. So that's how to deal with natural logs and common logarithms. Evaluating a logarithm, again, it may mean that you have to use the change of base formula. So, you know, if you had log base 5 of 10, well, how would I do that? I could do just straight up log of 10 divided by straight up log of 5, right? And you can just put that in your calculator and get an answer. There are some logarithms that you really don't need a calculator for at all. For example, let's say you wanted just the log of 10. And I want to figure out what this is. Well, I could type it in my calculator, but it's going to say that it's 1. And somebody could say, well, hey, Mr. Mulcash, how'd you know that was 1? Well, the reason why I know it's 1 is because the base, remember, is automatically 10. What's the exponent that makes 10 into 10? The exponent is 1. 10 to the 1 is 10. So what if we had the log of 100? Well, that would equal 2 because 10 squared is 100. So one thing you should remember about logarithms is that every logarithm is equal to an exponent. The exponent goes on top of the 10. Excuse me for a second. Okay. The exponent goes on top of a 10. 10 to the 2 is equal to 100. So that's kind of how that works out. Okay. So now what we're going to do is we're going to talk about properties of logarithms. There are some properties of logarithms that you can use to manipulate logs. So there's 4 of them, in fact, and I'll just go ahead and tell you what they are. So property number 1, log any base of a product. If 2 things are multiplied as an argument, you can split this apart into 2 separate logarithms that are added. So the base stays the same. The individual factors that make up the product go in separate logarithms, and all the logarithms are added together. And I don't have time to prove why this works, You can Google the proof for this if you want, but basically the reason why this works is because these two things are exponents. Remember, every logarithm is equal to an exponent. So why would you add exponents? Probably because you're multiplying expressions that have like bases. Like for example, if you had x squared times x to the fifth, this would be x to the seventh. Well, what did we do to get the 7? We added the exponents. That's kind of what we're doing here. There's a similar product, which is a direct consequence of this. Or sorry, not product, but property. What happens if we're dividing? Well, if you divide two factors, two quantities, they're not called factors anymore, but if you divide two quantities inside of a logarithm, you can still put them in separate logarithms, but instead of adding, you subtract. And the reason why that works out is because, for example, if you had x to the fifth divided by x squared, you would subtract the exponents, right? 5 minus 2. So essentially what you're doing here is you're subtracting two exponents. It's a weird look for an exponent, but that's what a logarithm really is. All right, and then the third one, okay, so this is called the product property. This is called the quotient property. The last one is called the power property, or the power rule. So let's say that we have this m here, and n, little n, is an exponent. What you can do is you can take the m away from the exponent, and there are n of these things multiplied together, so you can repeat this rule over and over and over again. You can add it out n number of times. Well, instead of adding it n number of times, we can just multiply it by n. So this power rule says I can take this exponent that's in the argument and move it out in front of the logarithm and multiply it by the logarithm. That's the basic properties of logarithms. Okay, so there's two ways that this can be used, and we'll talk about those real quickly with a couple of examples before we end this video. If I'm going too fast, feel free to pause, rewind, or whatever. Let's say that we have this expression, log base 3 of xy, and it says expand this. Well, x and y are multiplied together, so we'd use that first property, right? You do log base 3 of x plus log base 3 of y, and you're done. That's it. One factor is an argument, one factor is an argument, same base, add, you're done. Okay? What if the x was squared? How would that change the answer? Well, you do the same thing. You do log base 3 of x squared plus log base 3 of y, but there's one extra thing you can do. You can use that third property to move this exponent out in front. So this is completely expanded out. Okay, completely. And of course, you can get really creative with stuff like this. So, for example, log base 3 of the square root of x. Okay, that's the same thing as raising x to the 1/2 power. And so you can take your 1/2 out in front of the logarithm. Right? That's how you would expand that. So, Alex will take you through in greater detail what I'm talking about here, and you'll get much more practice than what I'm showing you here. Right now, I'm just kind of giving you a basic overview. So that's expanding a logarithm. Now, there's another thing you can do with these properties. You can go the exact reverse way. So let's say that we want to write expression as a single logarithm. So let's say we have an expression that's got bunches of logs in it, and there's numbers multiplied by the logs, and they're added and subtracted and multiplied and all this wonderful stuff, right? So for example, let's say we have 3 log base 2 of x minus 4 log base 2 of y. So all the properties that we used, that we showed you earlier, you just take these numbers that are in front of the logarithms and put them back up as exponents, right? So this becomes log base 2 of x cubed, and then this other one becomes log base 2 of y to the fourth. So now that the coefficients of the logarithms are gone, we're subtracting two logarithms that have the same base. So what we're going to do is divide the new arguments in a single logarithm. So the numerator of this is going to be x cubed, and the denominator is going to be y to the fourth. And we now have a single logarithm, so this is our answer. So essentially what we're doing here is what I did just a little while ago, but in reverse. We can take this and we can split it apart, first by using the quotient rule and then using the power property. But you can also do this whole thing in reverse. Okay, so that's what you're going to be doing in ALEKS this week. This is a little bit weird, I get that. Many of you haven't probably seen a logarithm since high school, or when you did go through logarithms in a previous math class, all this was very confusing. So spend time going through this video in great detail, and if you're in my Math 171 class, use ALEKS the way you're supposed to. Don't rush through it, okay? If you have a question, don't forget that you can email me, or you can ask Mr. Molikash in the discussion board. So have a great week. See you next time.